Now I will introduce the architecture of AlphaGo-like schemes. Basically, there are two key components of AlphaGo-like schemes. The first of which is a convolutional neural network, where the intuition or knowledge of how to play the game Go is stored. Such knowledge is obtained by training via self-played games or human-played games, or a combination of both. With this knowledge, the neural network will be able to give recommendations of possible moves based on a board state. These possible moves are fed into a multi-color tree search algorithm, where these moves are examined, and eventually one is selected as the final move based on certain criteria. Here is the neural network. As you can see, there are input, the hidden layers of the neural network, and the output. The input is the game state. For example, here, there's black to play. On the very top layer, the ones mark the black stone's position, and if there's no black stones, there are zeros. Below the surface layer, there are previous moves of the black and white movements. The bottom two are also marked either black are going to play or white are going to play. So the input is the game state. After the neural network does some processing, they can output two things. The first is the vector P. So this vector includes the likely possible moves and their probabilities of being chosen. For example, if you the picture here, the spot 3A, that's the most likely move to be chosen with a probability of 91.6%. And 5D would be the second favorable choice. Okay? So the second output is a numeric value, V, also known as the win rate. It's the estimated probability of winning given the current situation. The value of V could be ranging from -1 to +1, where the -1 stands for a loss, 0 stands for a tie, and +1 stands for a win. Now we come to the multi-color tree search. So the search is based on the current game state, right? For example, here we have 3 possible moves. Then we're going to choose the move that has the ability to maximize Q plus U. First, we'll talk about what is Q. Remember, for each node here, each move here, they have an estimated probability of winning. So the summary of the possible winning from the next states here and here, it's the W for the node of this one. And because this route maybe have visited for a number of times, which represent N. So the Q is going to be the average of W over the time being visited. So again here, Q is the estimated probability, sum of the winning probability divided by the times being visited. Obviously, Q is very important because it's the confidence that you're going to win the game. And then the second factor is U. So this one targets a different kind of aspect because sometimes a confident move may not be the best move or the optimal move. As a result, during the training stage, you definitely want to explore other possible moves. So that's why U come into place. Here, that's the function for U. Roughly, if you see this portion, the N as the denominator, the larger N is, this portion can have a smaller value. Okay? During training, if you want the AI to explore more untouched territories, you can amplify this effect by using a larger C. In competition, of course, you can use a smaller C to rely on more about the winning probability values. So you want to strike a balance between the exploitation and exploration. So eventually, the move with the highest Q plus U will be selected. Here, we're going to talk about the training process. Initially, there's random parameters in the neural network. So you're going to generate a number of self-played games. After each played games, you can assess the outcome. Here we see here. So after the game finished, of course, we can know the actual outcome based on the rules of the Go. So we have a predicted outcome, which is V, and we have the outcome Z. To make our network better, we would like to minimize the difference between the actual outcome and the predicted outcome. In addition, we also want to maximize the similarity between the actual move and the predicted move. So together, we wanted to minimize the difference. The last parameter is a C to prevent overfitting. Now we go back. So after self-play games, and we adjust the network parameters to minimize the difference and maximize the similarity, right? So we get a new generation of AI. This new generation is a new network. It's going to compete against the current best network. If the new network is better, then the new network becomes the current best one. You can repeat this process until a desirable agent is obtained.